All right, yeah. I don't know why I still have those overview. Oh, I unpublished a bunch of them. That's useful. I should probably start doing that. And the other ones /delete them. All right. So hopefully you've had the chance to watch these Big O videos. If you haven't, please take a look at them and watch them. The first one I go with a general overview, and I go over, and basically what we're trying to do is establish not the mathematical foundations of runtime complexity. Unpausing. So if you're interested, this is the textbook from your this is the draft, I think, of the textbook that's used in 3223. If you're interested in all of the whole mathematics behind Big O notation, and you haven't gone through it yet, Dasgupta's algorithms is pretty good with the overall mathematics of it, but we're not here for the mathematics. You're supposed to cover this not in 3223, but a class before that, which is 2166, which means if you're an IST, you're not taking that, right? And again, this is the more mathematically kind of not complex, but rigorous part, right? We're not going for rigor in this class. What we're going for is kind of, for want of a better word, the feel, for you to understand that what I'm talking about between constant, linear, and quadratic time. The idea here is that measuring algorithms is kind of a mess in terms of like just trying to chart times on a computer, right? You can't just simply run it on a computer and one algorithm on one computer, run an algorithm on another computer and say, okay, this algorithm's better than another. Even if you have like two MacBooks made in the same year, right, with the same specification, because you might have your install set up a bit different than somebody else, your OS might schedule things differently, which means that there might be some inconsistency in your runtimes. Okay, so we don't generally measure runtime in seconds when we're trying to compare algorithms, because again, hardware changes throughout the year, and so if I'm reading a paper from 10 years ago that says, hey, this took this long to run, that doesn't necessarily tell me much about what it would run today. This gives me a lot more useful information, though, or a lot of you. It's not bad, but this kind of thing gives me useful information, the Big O notation, which simply says what is kind of the speed of growth of an algorithm as the workload increases. So let's talk about lists and arrays. Like, let's assume that, like, for an algorithm, we have an input of that's some certain size, right? And that size is n. Then we basically in this kind of part of the semester, we're concerning ourselves with runtimes of three different types. We've got linear, constant, and quadratic. A constant runtime basically means it doesn't matter how big the list is that we're passing in. The algorithm's going to take the same amount of time no matter what, right? It could take a really long time, right? It could take a really long time, but it would take a really long time on a small list and a really long time on a big list. In fact, the same amount of long time is the idea here. So one example, but typically it's much faster. One example of this is the size function, right? Getting the size of an array or array list takes basically no time whatsoever. It's just a query of a variable. It doesn't matter how big the size is. And that on the flip side, what if I were to go through and individually count every item? Like individually, just one at a time, go through and count rather than calling the size function. That would take me O of n time. What does that mean? That means it takes me a linear amount of time. O of n means we grow at a linear rate. That means that if I double the size of my list, it means it doubles the amount of workload I have. Think about like what I have to do for a second when I get an exam. If I've got 30 students, it's going to take me 30 students worth of work to get through. If I now have to teach another 30 students, right? I've doubled the amount of students I've got a grade. It's going to take me twice as long, right? Twice as many students means twice as long, all right? On the flip side, Let's say, though, that I am extremely paranoid about plagiarism and cheating on the exam, okay? So let's go back to those 30 students. I'm going to grade the student, and I'm going to check every single one of his answers against every other one of the student's answers. So for every student, I'm comparing his exam to every other student's because I'm paranoid and don't trust my students, which leads to a very hostile relationship. So no, it's not how it typically works. But let's say I'm comparing. But so for this student, I'm comparing against 29 other students, and then for this student, I'm comparing him against 29 other students, and this student, I'm comparing him against 29 other students. All right. Now let's assume that, again, I'm teaching 2 sections instead of 1 section. Now I have twice as many students, right? The original amount of checks I needed to make was somewhere around the order of, if I had 30 students, I had to check it against 29 other students, right? And I had to do that 30 times. So I'm checking 29 students 30 times. Let's round up and call it 30, right? I was doing 30 squared checks. Now I'm doubling my input size. I'm doing twice as many students. I'm not doubling the amount of work I have to do. I am quadrupling the amount of work I have to do. I'm going from 30 to 60 essentially. Going from 30 squared to 60 squared, which if you think about that, right, 30 squared is 30 times it would be 30 squared times 2 squared. Multiply those together. So yeah, it gets to be a bit of a mess. Quadratic time is this. So when we're talking about run times, that n, basically the idea here is as things get really big, though, we don't care necessarily about kind of other factors that go in. Like, okay, for every item in the list, I have to run through it twice, 2n time. I don't really care about that. Because as we approach infinity, that's not really important. As we get the difference between 1 million items and 2 million items isn't that important, right? The difference between 1n and 2n isn't that important. The difference between a million and a million squared, though, that's a huge difference. That's what we care about. That's why so what we care about is, yeah, this might be worse for a bit. Something 2n plus 20 might be worse for a bit, but it doesn't take too long for n squared to be even worse. N squared isn't actually too bad of a runtime in a lot of examples. We often, for a lot of harder problems, n squared is the best we can do. But basically, if you can think of it like this, constant time, we're doing checks against, we're doing very simple checks that take the same amount of time no matter our input size. Linear time is basically something where it says, I have to do something for each item in the array, in the collection that I have in the array list. And if I double the amount of work, if I double my input size, I'm doubling the amount of work I have. N squared says, okay, for each item in the array, I'm basically comparing against every other item in the array, or every other item in the array list, right? So if I add one more item to the array, that means I basically have to do n more amount of work, because I have to do n more comparisons. So the result is that if I double the size, if I double my input size, I quadruple my workload. Okay. So that can be and if I go up by a factor of 10, I'm now going up by my workload goes up by a factor of 100. So that's quite disadvantageous. Now, one thing that I will note, though, is that we talk about this in terms of runtime efficiency. Big O can be used to measure other things. You'll see it often in algorithms that, if I go to merge sort on Wikipedia, over here, you'll see that, and Wikipedia is great for algorithms, very great for algorithms. First off, you'll get, for sorting algorithms, you'll get these great animations, but it'll say, hey, worst case performance, best case of performance. Yes, there's a big O, there's a big omega, and a big theta. We can get into those later, but those basically says, big O basically says, hey, it's never going to be any worse than this. Okay? Big theta basically says it's never going to be any better than this. So and then your big big omega. And big theta basically says it's neither going to be better nor worse than this. It's a much harder kind of mace. And end result, a lot of computer scientists and programmers use big O when they mean big theta, and that's okay. It just drives mathematicians insane. But anyway, what I was saying is that notice here that it's talking about performance, right? All these numbers and scary math symbols, whatever. Don't worry about that. What I wanted you to notice is also it says we also use big O for space complexity, meaning the amount of extra space you have to use. We don't typically measure that because these days, for a lot of applications, especially at this level, we don't care because space is cheap. Time is expensive because you can't buy any more of it. Literally cannot go to a store and buy more time. You can go to a store, buy more RAM, can't go and buy more time, right? Right? The seconds are ticking away and you cannot get them back. You should probably call your mother because, she'd appreciate that. Anyway, philosophical dread instilled. Let me talk about your homework. So go over the quizzes to make sure you've got that right. But this homework is a lot more like a mathematics homework, okay? Except the difference is that you're going to be demoing it. You don't turn it into me. I would like you to upload it to Canvas, personally. I used to have people hand it in. Honestly, it's easier if you just kind of like take pictures of it and upload it to Canvas. But the way you're going to get graded is the same way anyone else. I'm going to sit down next to you, and you're going to go through your answers. The difference is that if you're wrong, I'm going to tell you which ones you got wrong. I'm going to maybe tell you why you got them wrong, and I will go through, and you will get the chance to correct them so you can get 100 on this assignment. That's as opposed to a math where you hand it in and hope, and then you get it back, and then you don't get it, and then you don't work on it because you've got a bunch of other things to do. Yes.
Should we print it out, or is it okay if it's online?
Okay, if it's online. If your answers that you turn in is just a text file or a Word document, I prefer text, but if it's just a Word document that only has like one, the answer to one is this, the answer, one, answer, two, answer, three, answer, and you don't even bother including the questions, that's fine. I am super flexible about this one, okay? It's totally fine. A lot of students, what they do is that they'll often open up the PDF and use like Word or something to convert it into a document file and then do that, or edit the PDF. Also totally acceptable. Some students print it out, which honestly feels like the correct solution for math homework. But again, whatever you need. I'm very flexible about this one. Yes? I do not have a stapler on me.
I'm not a stapler.
Although I probably have some paper clips in my office. Paper clips are perfectly acceptable. It's fine. All right. So a couple notes. In this one, you're going to be going over and converting some t-evens, which is the traditional way we say the amount of time something takes given n items, right? You're going to be converting these t-evens into their big O notations. The rules for doing so are on the front page. So these first rules are what you care about for like doing your these two are what you care about for doing the first page, and this one is good advice generally speaking for the rest of the homework, which is counting the number of nested loops, right? If it's just a normal for loop, then it probably takes O of n time. If it has a loop inside of a loop, that's probably O of n. I say probably because there's some cases where if you're like skipping over items or doing weird jumps, it might be logarithmic, but that's not the case here. That's why I say usually. Unless you've taken calculus 2, you're going to get this one wrong, and that's okay. I'm going to go over 3 and 4, which are the ones you'll get wrong, in class on Thursday. You'll get an impromptu math lesson. Sorry, but I also enjoy doing it. These over here concern array lists. You can answer that, again, counting the number of loops or thinking about the number of items you have to affect or shift are very good. This one is basically is from a puzzle book I really enjoy, that I really enjoyed as a kid, that has maps and mazes. This one is I'm asking you basically to go to Wikipedia or Geeks for Geeks or some other website and basically say, hey, what is a Rudrada path or a Hamiltonian path? They're the same thing, by the way. They're just named differently because basically, it was basically discovered by a dude, Hamilton, and then also found out, and it was named a Hamiltonian path after him for the longest time until they discovered, hey, guy in India, Rudrada, discovered it centuries beforehand. So, as happens in mathematics. So, same name for basically the thing, and basically say, hey, and I'm asking basically, is this the same thing? And if so, why? And then kind of getting an idea here. If you get this wrong, I'll sit down with you and explain kind of different solutions to it. There's different justifications you can make. Bogosort, and finally Bogosort, which is famous. Bogosort is a famous sorting algorithm. It is one of two algorithms that exist only for pedagogical purposes, meaning that nobody actually uses them except for homework or exams like this. Bogosort is a terrible sorting algorithm. It simply says, hey, while your list isn't sorted, shuffle the list and check if it's right. Yes?
Does that mean that duplicate shuffles are allowed?
In the worst case scenario, yes. So that is a great question. So for worst case, I would assume that duplicate shuffles are allowed, meaning that you could get really unlucky and shuffle the same thing twice or thrice or quadrice. And with the average time, I would say here, assume that you're going to go through every single permutation of your list only once. Look it up on Wikipedia. You'll find the runtimes there. It's a very bad runtime, by the way. The other pedagogical sorting algorithm, by the way, which we won't go over in this class because it's mainly a 3223 thing, but I figure I bring it up here because not everybody introduces it, is stooge sort, inefficient recursive sorting algorithm. And it's very simple, which is that if the value at the start is larger than the value at the end, swap them. And then if there are 3 or more elements in the list, here's what you do. You stooge sort the first 2/3 of the list, you stooge sort the second 2/3, and then you stooge sort the first 2/3 of the list again. Okay? This is named after the Three Stooges, where they do a lot of slapstick comedy where they slap each other back and forth. So basically all the items in here just simply get slapped back and forth a whole lot. It's a very inefficient sorting algorithm, but the entire point is for you to learn in algorithms to learn how to do something called the master theorem, which is to be able to calculate, it's this runtime, which comes out to this nasty thing. So it's a very inefficient algorithm. The worst algorithms we typically use in production are O of n squared, and even then we only use them because sometimes they run in linear time. And Bogosort is worse than that. The final part of your homework is the meanest, maybe, which is basically, and my laziest, where I'm saying, hey, all those things you wrote for problem 2, for homework 2, do a big O analysis of them. At this point in your career, you will have written that your algorithm will be either, your answer is going to be constant time, linear time, or quadratic time. And I assure you did not write a constant time algorithm for any of those, so it's linear or quadratic. So again, counting the number of nested loops should help work for this one. My hint for you, though, is that if you're using a remove algorithm, right, if you're using a dot remove call, right, that means that you have to yank something out, which shifts all the items around, and that had a for loop in it, right? So just because you only wrote a single loop doesn't mean it isn't a nested loop if the method you called had a loop in it, right? So, let's see. Right, last bit. So, I hear one of the cynical ones of you thinking, but what do I need to know for the exam? What parts of this is relevant for the exam? So for the exam, this is not too much of my focus, but I will give you a heads up. For problems that look, on the exam, I'll have like 1 or 2 problems that look like what we have in the array list homework. Easier, though, than what I typically have. I consider them a bit easier problem because you're having to do them under a stressful, time-compressed circumstance. And typically they work like this. 10 points for the algorithm, 2 points for what was the runtime of what you just wrote. Okay? And then for another one, and then the other thing I use runtimes for is that for one of the harder problems, I think it's like 20-ish points, I say, hey, I want you to write this in O of n time, but if you can't, take a 5-point penalty and write it in whatever runtime you need, right? So if you can't find a way to do it in linear time, but you're like, well, it's obvious if I do it this way, but this way it's going to take quadratic time, take the 5-point hit, right? So basically it's a kind of it's a penalty, you might say, for not being, or a restriction or something, but basically it's part of the rubric there. And you get a nice big heads up about that for those specific problems. But it's also an option, but I don't make it a hard requirement because sometimes just simply getting an answer on an exam shows me that you understand the problem. And I'd rather you show me a not fully correct, I'd rather you show me a correct but inefficient answer than no answer at all. Because that's what your interviews care about. That's what interviews care about. All right, so with this one, I will go around and, help you out as need be / demo your assignments. I'm going to go ahead and stop recording and just go ahead and upload this so I don't forget about it later.